the blessings of the Almighty, and the presence of our respected dignitaries, we are gathered here once again for the second day of our national seminar on recent advances and new challenges in physics. It gives me immense pleasure to welcome our esteemed first luminary speakers, Dr. R.I.H.S BHOGRAI, BCS UP Budla Odisha, Professor Ashwini Kumar Raj, and our session chairperson, Professor Prabhanjan Mandi, MSCB University, Baripada, Odisha. Sir, please come to the stage.
I am very much thankful to the organizers for giving me the opportunity to present my work and also for chairing this session. Now, I request Professor R.I.H.S BHOGRAI to come to the class and deliver his talk. He will be talking on energy materials design using thermal vector process.
Good morning to all. My talk in ceramics. Okay. Department of Physics, this BSc Budla. Next minute. My outline of presentation is introduction, lectures, result, conclusion, or summary. Next. Hello. Let's look at these pictures. I think everybody aware of all the pictures. Somewhere, somehow we have made these pictures like that. From for construction from the base, or from refractory, or from melting and industrial ceramics, consumer goods. Have you seen all these pictures? Have you ever look at the just now you are sitting on the floor. So you see the tiles. Or that is construction from bricks, then paving, then sanitary ware with mass, all these are for the ceramics. Okay. Similarly, for refractories we can have high temperature ceramics, glass layers, non-ferrous concentrate or ferrous metal design. For consumer goods also we have fixed some plates, food on the plates, different types of ceramic plates. Shipping, tea, or those are called consumer products component of that. Then high tension and the industrial ceramics we have particle equipment, electronic batteries, all these things common. So you can say whatever you are using now it is apart from metals, we are on another kind of material in that is called ceramics. Okay, next. So what is ceramics? So you have to know what is ceramics. Just students side only I show you few slides. You are fundamental things. You don't have to read. Just like ceramic materials are inorganic, non-metallic materials made from compounds of metals and non-metals. Have you heard about metals and non-metals? This is into class 8 standard. Metals, non-metals. Can you anyone give given an which are metals, which are non-metals? Periodic table answer. Yes or no? So, core are metal, core are non-metal. Which are metals, which are non-metals? Answer anybody? No. Sir, that is why we don't think it's not for. Okay. So these ceramic materials may be crystalline or partial crystalline. Similarly, crystalline, our first concept is. Okay. So these ceramics are either crystalline or semi-crystalline. You can say partial. So what ceramics come from the Greek word ceramos, which means translated portable clay. classify these ceramics. Ceramics can be classified as glasses, which is concentrated in glass and glass, or clay products, which are structural clay products, or white wash, those was built in for plates and cups. Then refractory materials to be of the high temperature. Then abrasive materials, because the sandpaper material to clean the surfaces. That purpose is available. So compound ceramics, cutting, polishing, then cement and advanced ceramics. Most usually nowadays electronics branches we have to use advanced ceramics. From there, those ceramics also again we can distinguish so many ways we can classify. There are many ways we can classify the ceramics or groups into the ceramics. Another way can be traditional ceramics or advanced ceramics. Similarly, another way there is oxide ceramics, non-oxide ceramics, depending on the composition of the ceramics. So my focus is on oxide and non-oxide ceramics. All these other things, whether it's traditional ceramics or additional ceramics, advanced ceramics, for your purpose, you can go through the books, different books to get the. So now, presentation will be on the oxide ceramics. Okay. So what are the oxide ceramics? Again, oxide ceramics are divided into two categories. One is silicon ceramics and metal oxides. Scientific purpose, this I will focus on this oxide ceramics. What are the oxide ceramics? Why you are using oxide ceramics? Is that the oxidation resistance. It will not get oxidized. Those metals will not be oxidized. Then chemically not, electrically insulating, generally low thermal conductivity, and so that is why thermal conductivity is thermal conductivity. That type of things you are using. Low cost aluminum, more complex manufacturing of it. So, for non-oxide ceramics, these are the non-oxide, but our focus will be on the oxide ceramics. Next. Where to find the oxide ceramics? You can find oil industry, or you can find power generation, magnetic and electrical properties. You can explore magnetic, electrical, optical, or thermal properties to have more and more use of the ceramics. Then applications, if you look, that can go. There are high temperature, biomedical applications also there, so microwave applications are there, so different applications of these oxide ceramics. Now again, oxide ceramics are different, R.I.H.S, peroxides, and so on. But I will focus on the peroxide method. Peroxide method is those structure with the AB43. AX, BY, where A is the central atom. If you are identified the structure, then you can see what is the AB43 structure. That is A is the central part, B is the higher cations, okay, that is the cations with central edges of thing, and O3, that is the base. So then those peroxide metals, they can show you dielectric, ferroelectric, magnetic, or bigger. People, they explain all these properties for the use of ceramics. See, PbO3 or PbZrPiO3, these are these are called peroxide metals, and what are the properties we are explaining because which applications we are doing. Applications, suppose PbTiO3, they are piezoelectric, piezoelectric. If you think about the piezoelectric, piezoelectric, what are those piezoelectric? High temperature applications. Piezoelectric to apply some electricity content. You might have studied thermoelectricity, the fundamental of thermoelectricity. Okay, thermoelectricity Seebeck effect, piezoelectric effect works on the Seebeck effect. Okay. Similarly, dielectric or electro-optics, all these properties of this material can be exploited to use in the FT-lamps or FT-lamps and acoustic waves like that. Similarly, barium titanate, instead of lead titanate, we can have lead in toxic element. So people try to replace that lead with barium. We we can have medium tightening with similar properties. We can have sensors, multi-layer capacitors, and PTCR resistor, etc. These are all other bismuth ferrite. Okay. Most of these, if you apply most of the ceramic ones, people will work all these structures. Okay. These are called ferrite materials. Next. What is nine objective? Nine objective is so you have to be able to listen to it. Because as those who are in control, they can understand it. But people have to be very attention to listen. I have synthesized the bismuth molecule, bismuth oxide and lead titanium. Lead titanium is also oxide of the bismuth oxide also. So we can add this one, modify this lead titanium. Okay. In again, this bismuth oxide, this Zn and M can be replaced by Zn and Pi, another two metals. Okay. After preparation of this material, we can have some characterization between this SRT, all other characterization to see whether the material is firm or not and how we can exploit the properties of those materials. Then before that, actually, we are expecting something which we need because all this processing, we have to use the high temperature. Okay. So that is called one process is called sintering, then another is annealing. So the thermal temperature we can get methods. Now we use that vacuum annealing, another term is using vacuum annealing or direct and electrical studies. Okay. Then next. So these are the samples or the sample preparation. Last yesterday, I think MDK South has shown you a good pictorial representation of how samples are being prepared for the ceramic samples. Okay. So here I have two materials over here. Using this for that preparation of gold ceramic, I am using the raw materials are lead oxide, bismuth oxide, zinc oxide, silicon oxide, titanium oxide. For second group, I am applying lead oxide, bismuth oxide, zinc oxide. Instead of bismuth, I am using zinc oxide. Next. Why lead titanium I have prepared under that? So lead titanium is a ferroelectric substance have been quite used for capacity. The use of the lead synthesis for the capacity and water transistor or mixture and optoelectronics because of the high purity and high spontaneous polarization, non-linear optical activity, excellent dielectric, piezoelectric and bioelectric properties. Naturally, once we prepare a sample, we have to explore their different properties. So how to do it there? You have to enhance the physical properties or with the computational method or different way of synthesis method, either in a physical method or chemical method. Or we can influence the vacuum annealing with exotic properties. This structure is C. I have for the peroxide structure, how it looks like, PPTI. Okay. So PP1 is the, I can see, these are the PP atoms. Pi is the in between, O is the product. Next. So, all I need to be because how I prepare, I am skipping this one. Next. These are the which method I have prepared. As I told you, you can prepare in solution or different methods are there. Particularly for my case, I have used the solid-state gas where what I did, I have taken the compounds in stoichiometric, whatever the compound, the lead oxide, those compounds in stoichiometric means going as very different compounds to be there. Then I get ball milling machine. Ball milling machine means I can get one method where powder and ball will be mixed. Okay, thoroughly mixed with that. Then dry in oven. Then calcine heat it. The calcine is something you feed it with a furnace. Then after that you have to take the X-ray. X-ray diffraction method is used for the surface analysis. Whether tail production is there or not, whether that particular cell is found or not. Then filtration, sintering. Then after sintering, we have to vacuum annealing. Vacuuming when we have to evaporate the environment After the sample preparation, you use XRD, APSL, LCR method, all these instruments used for the various characterization techniques, various sort of. Now, I have two series. Now I talk about one, then summarize the other one. Okay. So just summarize one method again. Room temperature, electromagnetic, smooth, zinc, silver, and acid modified with lead packaging. Okay. Next. So for that, already I told you, I have taken bismuth oxide, lead oxide, zircon oxide, titanium oxide. Okay. All of them. Then sample after characterization, we have put the XRD for verification whether the compound has power. These are the XRD. You will get these where we will show you from the XRD method. You can see the crystal structure. What are the crystal structures we are getting? Then after the result, the finding what I like to show you. XRD pattern shows a single crystal without any impurity. Different things are intent alcohol, tetragonal structure. Whatever crystals are harmonic structures. Okay. So those crystals are from there, crystal structure, and that with the increasing composition, we are carrying the data with zircon. With the increasing of this one, dependent looking from zircon, the peaks are increasing. And from there you can calculate the ABC parameter for a crystal. You have to calculate ABC, that is called lattice parameters, ABC parameter, and angle state. Okay, crystal angle also, alpha beta gamma. So from there you can calculate alpha beta gamma and ABC parameter. Okay, you can find the volume of the crystals and the crystals, what are the crystal size also you can size. Next. So this plot is used for the crystal calculation and working formula. That the formula William Hall plot. This is for the William Hall where this calculation is made from this equation beta. Beta is equal to k lambda d cos theta plus 4 epsilon delta. What is this beta? Crystalline size, but k is constant I think, and epsilon k is the particles factor. From there, different crystalline size and strengths also to calculate. So to TM FEM, we will get the crystal cells. From second level, you cannot see, we will see our powders, but when in this powder, you will be not using a FPSM, you will get the and you can measure the crystal size. Microstructure we have out there. Then electrical properties I will concentrate on the electric structure, electrical and magnetic property. This is the electrical property is used for the calculation for particular frequency to the dielectric constant and the dielectric loss. So you can calculate what is the observe that the lower frequency, these are the lower frequency they will vary. So from lower frequency, phase charge, then to result in the polarization, which leads to the increase in the dielectric constant. Why dielectric constant increases? Similarly, for the dielectric cross, the dielectric cross is a long-term hopping mechanism, okay, where we are charged at cross across the plane boundaries. We are comparing here, one is your air energy, another one is vacuum energy. Air energy means centered in the room, the air temperature, air environment, and vacuum energy is centered in the nitrogen atmosphere. For all vacuum energy and air is both dielectric constant, here is capillary pressure and low temperature, but with the increase in the temperature, we will see that both dielectric constant increases. And this increase in the dielectric constant and air temperature is explained on the basis of interfacial polarization or defective as compared to dipolar polarization. The sharp increase in the dielectric constant and higher temperature also relates to thermally activated charge carriers or the contribution of oxygen vacancies. And the dielectric loss, if you look at the dielectric loss, within the dielectric loss, which temperature we use, temperature conduction process, and the high value dielectric loss because we need low dielectric loss, high dielectric value electrical property. You have to conductor power is equation known as the conductor power. But sigma is conductivity of the electric material. It will be so far equal to sigma is equal to any mu. Number of constants, electronic charge, mobility, and also now that has been modified with this law, or it will sigma S equal to AC conductivity equal to sigma DC plus A omega to the log n. Okay. Those are being plotted over here. Next. Then another relation also we can do R.I.H.S relation from where we can calculate the activation energy. This activation energy, you calculate activation, what is the activation energy, where the activation sigma is equal to sigma exponential of minus k by k. To calculate this EA, we need sigma to every t. Then only we can. So using those equations, we can calculate activation energy for different chemicals and for different compositions also. Okay. And this activation associated with the presence of oxygen vacancy in active and this residence with the oxygen vacancy due to the presence of free electrons which make the harmful interaction. P-type interaction is a polarization and we have from there we can calculate the force in field, then again this became R. Okay. All those calculations, it is better with this thing. These are the ferromagnetic. Magnetic property. What is the ferromagnetic property? Those two samples with this will show you this graph like this. What will happen? And the magnetic values, circulation magnetization will get in the EF1 graph. And luminant magnetization will calculate saturated magnetization. What is the saturated field? And the coefficient field for this one. So these oxygen from that those two property what we are going to record over here. We have prepared this one. It will have this record and we will do in-game analysis all this. Next. Second series, similar same, the only thing is the composition. Composition there we are comparing here over here and here. Okay. So I want to test. So finally you skip 4 slides. All that will show that okay, time constant, so better to skip all. And finally, so the second series we have this layered modified BJT sample. Okay, the structure similar that was the crystal structure. Then we have again vacuum analyzing air, those similar to what so all those things. I will give you a comparison figure. This is the summary of those two sample preparation. What we have calculated because we have seen that the thermodynamics, ABC parameter, we can calculate A equal to B, but not equal to C. So that is equal to C by A is we can calculate. So that we can calculate also alpha ABC, you know. So volume can calculate, then energy, epsilon maximum value of the particular electrical dielectric loss and maximum value dielectric loss, then magnetic polarization, then magnetic value. All the I have summarized over here, whatever the loss. Then we have seen that out of those two syringes, here you will see, all people will have deadline polarity, which is parameter 1 by 1 3. Volume. Then, so what we have seen that the parameters like dielectric constant, polarization, room temperature, permanent temperature are enhanced by the case of oxygen vacancy. And among all single cell samples, the last one, this sample got excellent dielectric constant value, maximum polarization, and ferromagnetism for possible application in memory device, actuator, or sensor. For all these devices, we can say the property which are needed are being enhanced. Okay. so also committee members of this R.I.H.S, especially student volunteers and student members. Those who are having patience to listen us. Okay.
Any questions from audience?
Hello, so, the last 2 days, I seminar କିଛି ତ ବୁଝିବ ନାହିଁ ସାର୍ କିଛି କହୁନ କିଛି କରିବା ତମେ ସଚ ବ୍ୟବହାର କରୁଛ କିନ୍ତୁ କେବେ କରିବାକୁ ଚେଷ୍ଟା କରୁନି ଆମର କାମ ହେଲା କିଛି ନୂଆ ବତେଇବୁ ନୂଆ ଦେଖେଇବୁ ତାପରେ ତମର କିଛି ଆଗ୍ରହ ବଢ଼ିବ ତମେ ଯଦି ଆଗ୍ରହ ନ କରିବ ଏଇ ସେମିନାର ମୂଲ୍ୟ କିଛି ରହିବନି କେତେ ଜଣ ତମେ ହାୟର ଷ୍ଟଡି କରିବ ଆଉ ଏଇଟା ତମେ ଦେଖା ହାତ ଦେଖିଲ କେତେ ଜଣ ବର୍ତ୍ତମାନ ହାୟର ଷ୍ଟଡି କରିବ ପିଏଚଡି ପରେ ଏମଏସସି ପିଏଚଡି କରିବ ଆଉ କେତେ ଜଣ ଓ ଠିକ୍ ହାତ ଦେଖୁନ पूरा मुझे बता दे भाई भाई नहीं जाने को नो क्वेश्चंस मैं क्या बता दो भाई थैंक यू अश्विनी कुमार
Hello. Can I have a better good morning here there? All of you, can I have a good morning? Come on, breakfast done? Yes, sir. I'm done, I'm full. Got done? Yes. Am I audible there? Yes. Great. So guys, what I want is, I want a great interaction between you and all. You can ask, stop anytime, ask questions. Are you excited with the topic? Hello? Are you excited with the topic? Yes. Can I have a better yes? Yes. Oh, wonderful. That's great. Breakfast is done, I can understand, right? Full of energy. Wonderful. So great. I'll take a couple of minutes to introduce myself. Myself, Dr. R.I.H.S. Right now, I'm acting as a CEO at one of the IT company, that is R.I.H.S Cloud Consulting. All the deliveries here, breakfast, everything, mostly to the academic side. Little other side of the table. Though I pretty closely work with academia as well. I'm acting as one of the guide under me, couple of people are doing research on the PhD and all. I'm pretty closely working with the academia, but primarily I'm running the other side of the table, that is industry, and mostly to IT. That's what I'm privileged to talk about AI, because my company, we work on cloud and AI. And 27 years back, when I learned physics, how many of you are probably be surprised to know that I'm an ex-student, I'm an alumni of R.I.H.S college. And I'm really feel proud and blessed that my teacher is sitting, who taught me. 27 years back, I was sitting like you, but we were not having audited lessons. I know how much pain, how much difficulties my professors went through when they taught me physics. Today morning I saw the labs, the equipments where we can do a lot of practicals, but our time it was not there. So it's not me, but the professors who taught me physics, how much pain, the difficulty they went through. And I'm sure you know that there is a topic called AI in physics. So when I came to know about this seminar, I was equally excited that how I can collaborate AI with physics. So when I talk to a couple of people, they say AI and physics, AI is a different IT, all this stuff. I say no, there is a topic in physics called AI. Long time back probably we learned, but yes, that time AI was not that much popular, a lot of research was not there, but now, a couple of years back probably this has been very popular and people started acting on this. So guys, what I'm trying to tell you that before I go to the topic, you might be excited to know what is there in the content, but I must tell you that 27 years back, when I was sitting like here, listening to the talk of the professor, and the guy, the boy who was a student at R.I.H.S after 27 years, standing in the stage and sitting in the degree over here, and I'm feeling proud of the place that I'm going. And guys, this guy, the way he's sitting, standing and talking, the next person could be you. So sir, I was talking about how many of you are excited to do the research, to do the PhD, and come forward and take the help from the dignitaries. So few hands were raised. I was going seeing back and seeing how many people are excited, right? So this is one story of a student of R.I.H.S and the next student would be you, right? So and you are in the right hand, officers are going to help you out. Yeah? Wonderful. So let me start with how many of you know about AI, heard about AI? Can I request we can separate some mics if they want to talk. Can I get that? If anybody they want to talk on the mic, I can listen to them. Yeah. How many of you heard about AI earlier? Raise your hand. I'm sure. Hello, guys. How many of you heard about AI before? Hey, I'm not going to ask questions. I'm just asking. Have you heard about it? Heard about AI? No. No. Anybody very small applications of AI. ChatGPT, you use it? Oh yes. Listen, very less people are using ChatGPT. Guys, AI can help you a lot in doing research also. So the dignitaries are here, they talked about doing PhD research and all. When people are doing research under me, I say, hey, time has changed. So typically people used to Google, go into a lot of articles are there. Now you go to put in the ChatGPT, perplexity, you get a lot of guesses. And which will be the starting point of yours, which can help you a lot doing more research on the topic and finding some good things about it. Agree guys? How many of you agree that? Is it not going to help you? Yes? I'm going to talk about the pros and cons and specific to physics as well. I did a bit of research on that, what could be done there, right? Wonderful. So quickly I'll progress with that, and when I talk about, I'm Shwini, and I did PCM from here, by the way, R.I.H.S. And then I did my master degree in IT, I completely moved. Then I did my PhD. Right now I'm running a company which works on the cloud and AI, and AI is probably the current and future and of every aspect of life, right? Use of physics or anything else, AI is going to be embedded and going to help people to do their job better. And I'm an author, I'm a coach, I do a lot of mentoring to people, to organizations, and I'm an Amazon best-selling author. I wrote a couple of books. This will be my pleasure, the permission that I can donate one book to the library of R.I.H.S with the permission. Probably thus you can come to the library and read about what I have written. Right? This is all about myself. And right now is cloud and AI. When I came to know about the seminar of the physics and AI is one of the topic, I thought about the name, or when physics meets AI. Yeah. So I thought to put a topic called when physics meets AI. Physics was there, AI was there, but it was like a very independent system. Nowadays, couple of years probably it has been evolved drastically. But now my topic is when physics meets AI. I want you to imagine beyond what we are doing right now in college, what could be done and what people are doing and how AI can help them to do the better. Right? So I want to bring a notice about an organization called CERN. Why? I'll tell you. This is an European organization who is doing nuclear research, nuclear research all over, right? The subparticles. So the CERN organization is a nuclear research organization. Basically it operates, how the largest particle of physics within the laboratory is working. Right? One more subdivision of CERN I am going to talk about. What they are doing, they are making the subparticles travel near the light speed, and they want to experience how the matter and energy behaves like a Big Bang. You heard of the Big Bang? How many of you heard of Big Bang? Hello, Big Bang. Big Bang. How we talked about theory, right? How the earth evolved, how the life came, how the collision happens, right? All this happens in the Big Bang. So in CERN, this organization, what they are doing, they are creating an experience how the matter and energy will behave by traveling the subparticles near the light speed and simulating like a Big Bang. So they want to understand, analyze when the Big Bang happened, how the energy, how the matter, how the particle behaved that time. They want to experience, they want to learn, they want to analyze, and they create some theory about that. This is what they are doing, right? So what is happening now? There's something called, I was talking about LHC, right? This is LHC, that's the Large Hadron Collider. What they are doing? The subparticles, as I said, they are making it travel in the light speed and colliding each other. Then they want to experience how they are behaving. And imagining what would have happened in the Big Bang. Because in the Big Bang, this thing happened that time, right? Okay. Now the new scientific from proving black holes. What about black holes, guys? I don't know, these terms are being jargon for you. What about black holes? Hello in the universe. Black holes? Hello? Guys, you guys have smartphones. What do you use? Reels, all this stuff you do. So rather, even in science, you should do all this, right? All the terminology, the new things, right? No more reels. Because you are into science, you are into research, right? You should do all this terminology, what is the black hole, how the behave, how the particle behave, how the energy is there, right? So AI is not just accelerating research. Is reshaping the way physics is practiced. Physics was there, but now what AI is going to do, this is going to reshape it. Right? Everybody is now experiencing the new thing that is AI. I will talk about how AI can help, what are the other side of the AI as well, right? So what they can do is they're raising the new questions and creating challenges that physics never imagined they would face. Now the scientists, I heard about yesterday a lot of dignitaries, a lot of qualified people came yesterday, right? So they never probably thought about how AI can come and influence the way traditionally they are doing it. Right? They never probably ever thought about it. Right? So you think about AI microscope. What do you do? The AI microscope for hidden patterns, vast data sets that human research might miss. So now you heard about microscope, right? You heard about microscope. Now the AI microscope is there. So they would detect the thin particles, right? Then you talk about the AI calculator. Hello, AI calculator. What do you do? Now this will function as a calculator for problems beyond 4 size calculation. AI can do the fractions of second complex calculation. AI can act as a guide. So AI can act as a guide pointing towards promising experiments and research. Now my scholars are doing, they are doing research by putting AI. What are the previous findings, what are the drawbacks? We do that traditionally, but now AI can help do that. But what does that mean? When one of the most exacting science embraced one of the fastest technologies. So now AI can collaborate with physics and make it faster. That's what we can think about that this is going to be. Okay. What we are going to talk about? This was just an introduction. How many are bored? You need some entertainment? Exciting? Yeah? What we are going to do? We are going to talk about the particle physics. We are going to talk about the quantum physics. Pretty new. Quantum physics, what about guys? Pretty new, right? Quantum physics is a new terminology has come out now. A lot of research is happening there, right? Astrophysics, cosmology, we are going to talk about. We are going to talk about the condensed matter materials. We are going to talk about the fusion energy. We are going to talk about the challenges and future, what could be next. Yeah, excited guys? This is the agenda we are going to talk about. Okay, the first part is the particle physics. Spotting needless and costly hairstyles. What are we doing? I talked about the LHC, right? So what they are doing, they are experimenting, generating about 30 petabytes of data. Think about how AI can help in nuclear reaction. How about petabyte? Anybody petabyte? Byte you know, right? Byte you know? Byte? Kilobyte? 1024, right? 1 kilobyte is 1024 byte. Then what happens? After kilobyte? You have megabyte. What happens? Again multiplied by 1024, right? Then megabytes after that? Terabyte. And then the petabyte. What I am trying to tell you, why I am telling all this? Through this I am telling what type of huge amount of data this nuclear reactor is going to experience. So approx 30 petabyte of data annually, which is, to give the Netflix, you know, right? Which is more than the Netflix entire movie library. Multiplied, you can multiply. You heard about Netflix, right? Web series, movies, and all. You all, right? It's a huge amount of data that you have, right? It is the entire Netflix library, whatever is there. Video videos are what, videos, data science, right? But if you look at how much data they need to analyze on that, and what they're doing, now physics build collaborate trigger system to decide what gets recorded, but AI is making those systems out of. So lot of analysis. So in AI we talk about something called predictive analysis. Heard about guys? Heard predictive analysis? So predictive analysis talks about depending on your past behavior and the data, what the future may come. This is going to be predictive. Predictive analysis is one of the AI. So how the data, the huge amount of data we have, right? Now how the data behave, and based on that, this is going to do some sort of analysis and going to predict this could be the future. Now think about the physicist may take a huge amount of time to do the analysis and imagine what could be the future based on this data. But with the AI, the life of them would be very easy. Say that, hey, this is the data you have, this is how the data behaved earlier. With the current and future, this could be the future trend. Trend analysis, by the way, one of the behavior of AI, and future analysis going to be. So now, the scientists, they're working on the data, they have a tough time to analyze, but with the AI, this is going to analyze and tell, hey, this is the probable behavior of the particle of the data in future under this circumstances. This is going to help them. So, this is how when physics meets AI, right? Physics is there, AI comes and what life becomes easier or not, that's what I'm going to talk about. Graph neutral networks. Map out tangled particle traps and detector, reconstructing events in way what classical algorithm structured. Now algorithm. So now you put algorithm to your data based on the basically predictive analysis is based on some algorithm. You put some algorithm based on that, some future trend, some future prediction is going to come. Then you have deep learning classifiers. So separate interesting events from mundane background noise. Sometimes spotting patterns physicists and not consider. Sometimes what happens is a human error can happen. Maybe a lot of data are there to analyze few particles, they ignored it. But these particles may have a bigger impact on the research they are doing. So AI will never ignore, right? AI is going to say that, hey, there is some particle which can be contribution to your analysis. So this is deep learning classifiers are there which AI can help you with that. The interpretability challenges. Okay, with the AI the challenges are there, of course it's there. It is not enough for the AI to say, here's something weird. We need to know why it thinks it's weird. Otherwise, we cannot discover. That's what the biggest nuclear reactor in European organization they talk about. So then it's not just what, but you have to think about why. Correct? The analysis came, but the scientists need to analyze why this type of outcome is coming. So you need to do deep learning and understand that, right? The tension between AI's pattern finding power and physics demand for interoperability runs throughout the field. Now, the demand is going to why this output has come, what is the reason of that? Now, what AI did, based on the data, they get some output. Now we need to do the why. We need to do the analysis, how come this output has come, why this has come. We need to analyze that. So the dream is that AI will flag subtle anomalies, tiny ripples in the data that hint a new particle or if it cracks the standard model, but physicists remain cautious about a black box solutions. So, I mean, in the end of my presentation, I have a finding where I mentioned that it's not only AI. AI is a new, latest future, but this is not only the AI, or this is not just only the physics, but the right marriage has to happen, the right collaboration has to happen to find the best outcome. Right? Okay. Quantum labs, AI is powered. So what you have, if higher energy physics is about dealing with too much data, physics, I talked about how much 30 petabytes of data, which is multipliers of the Netflix library, right? It's a huge amount of data they need to analyze, right? Quantum physics is about wrestling with problems too hard to compute. I'm sure physics is a lot of complex computation, right? A lot of algorithms to solve it, right? The equation of quantum mechanics can, in principle, describe everything from polygon to subconductor, superconductor level. But in practice, the math becomes impossible as the number of particles grows. So you might be doing calculations in the traditional way, but when the huge amount of data is coming, math becomes very complex. It's too tedious to do all this, and where AI can help to contribute there. So one is neutral network quantum states. So mimic wave functions for many body systems, letting researchers model materials and where ones out of reach. One problem was out of reach, but now AI can go down in detail and dig out and find out and say that hey, this could be the contribution for your research and for the analysis. And reinforces the learning. So figures out how to control delicate quantum systems, stabilizing qubits against noise essential for quantum computers. So quantum physics is again one of the upcoming area. Physicists have put on more interest on there, and there also we can contribute there. Yeah. Okay. Now a two-way street. It's a two-way street. What is that? Why AI helps physicists build quantum computers? Fine. Quantum computers may one day turbocharge AI. Right? So it's a symbolic relationship actually. It's actually symbolic relationships. AI algorithm optimize quantum hardware design. So AI has its own algorithm. What they can do, they can help it. AI can help control and stabilize quantum system. Quantum computers could eventually train AI. Okay, by the way, interesting. People talk about AI is automation, but actually you need to train it. Remember, guys, you need to train AI how this is going to behave. So you have artificial intelligence in place. To use this in the physics research or any future work, you need to train it so that based on your training, this is going to behave. So what we do in IT when we build some AI agents, we create some AI agents. What it does, you need to train. Even guys, if you are using very small AI, ChatGPT for example, you need to train ChatGPT. So I put a LinkedIn post. I give it some prompt to ChatGPT writes a letter for me, write a post for me. Now when continuously I do, next time I give a command, it automatically picks up my name, automatically picks up my company name. How? Because the AI is being trained depending on what input I am doing. So there is a misconception. People think, oh, AI is there, my work is automated, nothing to be done. AI cannot do alone. You have to train him, not him or her, training right? You have to train so that based on your input, data, what you are working on the AI, it will be trained and more meaningful, better analytical, more predictive analysis is going to be. Right? You have to train the AI. Quantum machine learning might solve problems currently intractable for both the field. So this creates a feedback loop where each technology pushes the other. So again, so AI pushes physics to move, and physics with the help of physics not with the help of weather, physics trains AI to get the better work, better out of it. You got my point, guys? AI helps, but how is it going to help? The physicist has to train AI to get the better work. So it's a collaborative. It's not AI has come. People say okay, misconception. AI has come. Job will not be there. Not a job will be vanishes. But actually, it's a collaboration. So better skilled manpower is going to be used in various fields, right? Okay. Next is our eyes on the sky. What about astrophysics? So my point is how AI can contribute to different fields fields of the physics, right? So astrophysics is one of the field about. Anybody heard about it? Raise your hand. No questions should be asked. You can raise your hand. Astrophysics, have you heard about it? Hello? So I used to talk a lot when I was a student. Dilip sir can comment on that. So today the students don't talk. Hello? Today I like the students don't talk. What about astrophysics? No? No? If nobody raising hand means no, huh? Okay. Anyway, so it talks about when the first gravitational waves repelled through the earth in 2015. LIGO's detector barely picked up the faint signal. So, we are not able to track the signals. Now, how AI then going to contribute over here, right? So now AI algorithm is trained. Again, I'm giving stress on the word called trained. AI has to be trained in this. So now AI algorithm trained on simulated waveform. Okay, think about it. I told you Big Bang, right? Big Bang actually happened. How the earth created, life started. Now you want to experience that. How to do that? You have to create some sort of that type of simulated environment, right? You can stop. It is signal if I am going too much that right. Please, sorry. So Big Bang happened. You cannot recreate the Big Bang actually, because this is the entire swelling of the lives, earth, and everything, right? Solar system there, right? Now you want to simulate, think about, as I said to you earlier, I want you to imagine not what you are studying right now, but what is happening in the world. So I said CRN, the world's biggest nuclear reactor, right? This is a huge amount of data analysis is happening. Just think about, you want to analyze how the Big Bang happened. It is beyond imagination. You can't do that. Because Big Bang is gone. I mean, you can recreate it. But what you are doing? You are recreating inside the lab. Hello guys, I can think about. You are recreating the Big Bang in a lab. So how to do that? The subparticles, you have to travel in such a high speed, near light speed, and collide each other and understand how these particles are behaving. What would have happened there? And for that, lot of data, huge amount of data, lot of analysis, real-time work is happening. Though you are simulating it, all this is happening, right? So your AI algorithm to be created. AI is to be trained to understand that type of data behavior. When the data behavior is happening, because when this goes in such a speed, light speed, how the data is behaving, AI is to be trained to understand that. Some algorithm to be put, right? And this is happening, some signals near real time, fast enough to alert astronomers to swing their telescope toward merging neutron stars or black holes. So what is going to happen? How AI is going to do? So AI is going to analyze and automatically move your telescopes towards those areas where maybe they are predicting or they are analyzing this type of event is going to happen. Where? Astrophysics, right? We are talking about. We are talking about astrophysics, the sky. So in the sky, when such phenomenon is happening, we need to automatically the telescope is going to move and capture those moments and transfer to the lab for the further analysis. Excited guys? Exciting? Things are happening in physics, isn't it? Guys, is it exciting? So when it is exciting, I shout yes. You are saying yes. Is it exciting guys? Yeah. Exciting things are happening in the world, right? And you would be part of that in future. You are a science student, right? Okay. Now AI emulating cosmology. Now cosmologists are using AI emulator to stand in for expensive simulation for galaxy formation and dark matter. More complex galaxy, dark matters, quickly. Have you heard about now scientists has found water particles inside the universe? Anybody heard about? Quick. Have you heard about this news? The scientist has found water particles within the universe. and it reminded me in our Sanatan culture it was there. You remember? Some Rakshas came and took the earth into water. Then Vishnu came and took it out, Varaha Avatar. Heard about this? In Varaha Avatar, what they did? They took the earth into the water and came, this is cosmic water. This is cosmic water, now they found it. Now think about, if you have to analyze those, you need to get this data and analyze. Do you think the traditional way can do that? Almost impossible, probably. Very difficult, I would say. But with the AI, you can do that for sure, right? And we can order better. Move fusion dreams and plasma nightmares. You can talk about. You can have an AI control system. You can have a disruption prediction. I say AI works in the predictive behavior, right? Predictive analysis. So if any disruption is going to come, this can predict. AI model can warn you that with this based on the prior analysis, this could be coming, right? Prediction can happen. AI can predict you pretty better way, right? And you can do smarter experiments, faster physics. So your material science, your X-ray, crystallography, your X-ray, all AI can contribute there. So beyond the big headline grabbing areas, AI is changing every day physics labs. So you can install your AI into your physics labs and contribute a lot, right? The flip side, okay, new challenge has come. Now because AI comes, the new challenge can be the black box data. So deep learning model may spit out correct answers, but their inner working are. So now if you are the scientists, the physicists, they might say, we cannot completely rely on the AI alone. We may not completely rely on the AI alone. Right? This is the black box dilemma you can say about it. Reproducibility and risk. Physics demands reproducibility, but AI model trained on different data sets. So AI will say, what data you are giving, how you have trained me, I'll behave that way. That's what AI talks about. Then you have a simulation trap. Many AI models are trained on simulated data, but physics will say what? Will work on the actual data, right? And energy and equity, ironically, training massive AI model consume lot of amount of electricity as well. Now a new scientific symbiosis is here. Few people say that AI may help physics rediscover philosophical roots by forcing scientists to go grapple with these means understand versus predict. So AI is more into predict, but physics they more focus on the understanding of, right? This is one challenge being created. So physicists will bring the critical piece, the ability to ask meaningful questions. That is very critical. Ask meaningful questions to connect pattern to physics laws and to judge when results may make sense. And what is the road ahead? The road ahead, what can be done? One, the marriage of AI and physics is still young. So when people newly married, they struggle, they need to understand the compatibility, right? All these things are right now, right? So going future, new future, AI can guide the telescope, astronomically scan the sky, all this stuff can be done, immediately probably. In mid-term, quantum computing can happen. In the long term, fusion reactors can use AI, right? All this stuff you can in future can happen, right? The lesson of humility. One lesson is that from physics, that is humility. Nature has a way to survive. So what you are saying, AI may be a powerful tool, but it won't ever replace the human imagination. This will never ever do that, right? So ends skepticism that never driven centuries. Instead, the future looks collaborative. So it's a human and in big questions, and AI sifting through the noise and together closer about things. They can do the right marriage, right collaboration, and to do that. Right? AI is not just helping physicists to do their job faster, it's changing what it means to the physics setup. So right balance, right collaboration can help to bring the where research and invention and experiments are happening. Collaborating together is bringing in. So the future of the physics will be shaped not by humans or AI alone, but by their collaboration. So together they can do the collaboration, and that's what I wanted to talk about today. Thank you very much. And to tell you that, how many of you will be surprised? This PPT has been created by the AI, giving the right prompt, right command. This entire PPT has been created with the help of AI. Yeah? Thank you very much. I will open for the questions you can. Any questions?
Hello sir, I am a PhD scholar here. So I want to ask how AI can help me to write things like paper or thesis or reading literature. So what would be your suggestion?
Wonderful. There is one upcoming skills which is emerging, something called prompt engineering. How AI works. So you know Google, right? You search in the Google. Couple of years back, I used to search also. Now I have forgotten to search in the Google. It's all ChatGPT, Perplexity. These are the AI tools are there, right? So you need to learn one thing, something called prompt engineering, to give the right prompt. Because as we say, talk about specifically to the physics, AI cannot work alone. Cannot work. So you have to train it. So now you have to tell how the outcome will be different. For example, I'll tell you. This slide, that is a thank you slide. Okay? At the end, there is a thank you slide. That is a thank you slide is there. Generate this image. I give a prompt to AI. I say, so this prompt is very clear. I say that create an image for the slide of my presentation, which will say thank you. The theme I give is AI and physics. If you look at the images I put in, then which talks about prediction, analysis, depicting AI. If you look at all other pictures are there, this is more about physics. So I give a prompt to AI, say that I want to create an image which is a thanking slide to my audience, but bring it together. The theme is AI and physics together and create some image. So what I'm trying to tell you that start using the tools which comes free as well. ChatGPT is free, Perplexity is free. If you have a Airtel connection, they give you Perplexity free of connection. Free they will charge. Even ChatGPT also they give free. There is a paid version which I have it, but free version is enough for a student to start doing. Now you could start giving commands on various topics, and this will give you output. Okay. Instead of ChatGPT, you can go and tell that who is Dr. Ashwini Kumar. Really go there and put it. They will tell you about my entire biodata. So obviously the data is there in the different places they are going to analyze, right? So to answer your query, you need to start giving a right prompt, right? And specifically for research and learning, in ChatGPT also there is a writing tool is there. I am author. Now I have started using ChatGPT for my books writing also. Because when I am writing probably, what I struggle is I am using English word, but when I write that story, that word may not be perfect. There is a better word which I am not aware of. I am science English little bit of weak. So what I do, ChatGPT is going to give me the right English word, which will replace this word with a better word. Right? So even when people do research, the PhD degree, they do thesis writing also, you can start giving command that this is going to write the entire paper. You, for testing purpose, you take a topic, random astrophysics, quantum physics, whatever you do that, and you write, please give me article on quantum physics. Suppose you want to write article, right, in a magazine. They are restricted to 200 words, 500 words. You write that. Otherwise, there will be huge that, they're going to give you that. Then they also give you conversational communication. Then they'll tell you, do you want some graphics to be created? Do you want some site images to be created? If you say yes, then you create. Then you start it. So through that, you are actually training your AI. You are training your AI, and they are learning. They are also learning. AI is also learning what is your requirement. Next time you do, they will adopt those style and train it. Like what is here. Does it understand very?
Yes, sir. I got it. Thank you.
Thank you.
Sir, another question. Sir, what may be the drawbacks that can be happened by using AI?
Interesting, because people, when new thing comes, people talk about a good thing about that. But we need to know also what the drawbacks, right? People say humans involved in any area may be drastically came down because AI is going to do the job, right? Though the intention of AI is to train people so that they can do better work. Let me tell you the technology we work that is on Salesforce, it's a cloud. It's a US-based company. 2 days back, they laid off 4,000 employees because AI is doing the work. AI is doing the work. That is one. But with the right skill, now if I am working, I have to adopt this new technology within myself so that I am in safe place. I have to adopt it. So what are the new technologies I have to adopt? That is one drawback I can think about. Number two, AI outcomes are not always exact. You cannot completely rely on it. As I said, now these are predictive, mostly predictive. Now look at here, all the dignitaries, they are doing experiments, they are doing research. Can they rely on the just predictability? I just cannot rely on the predictability. I have to go by the data, by the truth. So relying on the predictability cannot be always possible. So this is why when I get some output from the AI, right now I cross-check twice. So people, what they do, AI is giving something complex. If they do that, then drastically might be wrong somewhere. So still, unless the AI is not trained exactly for looking at it, still you cannot trust 100%. This can help you can take it, but then you have to put more analysis to that and put in factors. So still now, AI is also like a newborn baby right now. In a couple of years, it's not yet well trained, so that is one area you cannot completely rely on. So that is for the second item. And complex algorithm. So we have to spend good amount of time to train it. Suppose I am doing very complex experiment in physics. Now I say that okay, AI is going to help me, just I put the data, whatever I do that. Because I have to create algorithm. Tell AI to use this algorithm, which can be useful in my experiment. And which will take some time, spend a good amount of time. But yes, one day is a trend, for future your life will be easier. But initially a lot of time to spend to train the AI, put the algorithm, right algorithm, so that AI can work. Sir, could I?
Now thanks for asking.
Sir, one question, sir. Yes, sir. Sir, give us a complete roadmap. What should be useful for the BSc student like us? Then to well organized in quantum computing, like give us any well organized roadmap that can help us in a proper way. And the best language which can be used in computer model in various way of physics. Best language and computer roadmap.
I could not understood properly, but what I have understood is your question was, as a BSc student, what do you think?
How can we use AI in a proper way? If we use AI, then we must have to know any language, coding language, means Scilab or Python, anything else. What should be the the proper language for physics for BSc students?
Okay. For AI, there are no restriction to languages, but if you ask me few languages, Python is very well equipped to handle complex algorithms. Nowadays, Python is very popular. If you are interested on learning some computer languages where you can build some AI, in physics area, Python language is definitely going to do that. Python is something you can rely on. And Python is just a language, but you need to have some sort of backend where the data storage is going to happen. A lot of data clouds are being incorporated now. So I think it's in the early stage, but yes, as early is better. You start learning which section of physics you want to focus on and how artificial intelligence can go there, and start learning the algorithm is very important. And yes, language is going to get good. Python type of language is going to have to learn.
Thank you, sir.
AI and ML. In ML, mostly Python helps a lot. Thank you.
Speaker will say.
Thank you, sir. Now, Professor Prabhajit Malik, MSc University Curricular Officer, give his talk. Thank you.
Good morning, everybody. First of all, I am thankful to the organizers for giving me the opportunity to deliver my talk. I will talk implications of metals and nanostructures for spectrometry and antiferromagnetic spectrometry applications. I will talk on the nanostructures, then I will discuss about the importance of metal oxide, then synthesis of nanostructures, and I will give a brief overview of spectrometry. Then I will apply for synthesis method to synthesis the important class of metal oxide like nickel oxide and zinc oxide, and its implication in spectrometry. Finally, I will discuss about antiferromagnetic spectrometry and the studying materials, how they can be useful for antiferromagnetic spectrometry applications. So nanotechnology deals with, since we are discussing about the nanostructures materials, I am going to discuss about the nanotechnology and related informations. So nanotechnology deals with the manipulation and control of substances at nanometric level. 1 nanometer is about 1 millionth of a meter. So physical and chemical properties such as mechanical, electrical, optical, thermal, and other properties are changed when you reduce the size of the materials. Nanometric system shows tremendous implications for the developments of devices like sensors, photodetectors, drug delivery devices, high density memory devices, applications. So this slide shows the different materials either naturally available or that made by man, showing the different length scales. So this range is particularly nanometric levels, that is from 1 nanometer to 100 nanometer. Some of the materials are already exist in the nature and some will prepare. So if you go for classifying the system based on the dimension, if you take the 3-dimensional object, you take a book, bigger book, that is 3-dimensional object, and you will consider a page, that is considered as a 2-dimensional object. If you take 3-dimensional object and go on reducing the size in 1 dimension, so you will get with 2-dimensional object. So similarly, if you further reduce in another dimension, we will get with the 1-dimensional object. And if you reduce the object in all the 3 dimension. As far as quantum confinement effect is concerned, in this relation, in this system, there is no quantum confinement. That is, electron can freely move in all 3 directions. So there is unconfined dimensions are 3. If you consider 2-dimensional object, that means we are reducing the dimension in one side. So we left with 2 directions. That means electrons can move in 2 different directions. Similarly, we have 1-dimensional object like wire structure. Then we have reduced the dimension in 2 different directions. So electrons motion is confined in 2 directions, and then unconfined dimension is 1. ଯେତିକିଟା ଆମେ ଯେତେବେଳେ 3 dimensional object କଲା, ଆମେ ଯଦି reduce ଯୋଉ ଗୁଡାକ direction reduce କରିବା, ଆମର ଗୋଟେ applications mostly ଯେତେ ସବୁ ଆମର inorganic system ରେ study होଉଛି, mostly metal oxide base ରେ ସବୁ ଯେହେତୁ ତାର ବିଭିନ୍ନ application होଉଛି, ବେଶୀ research metal oxide ଉପରେ होଉଛି. So since synthesis methods are different from one method to another, but they are categorized under 2 categories. One is top-down approach, another is bottom-up approach. Top-down approach कौन? हम एक बड़ा system ले लो, ताकि आगे वाले छोटे लेवल ultimately small dimension में पहुँचो, nanoparticle systems. Mostly physics people of physical molecular level to धीरे-धीरे ताकि crystallize करके nanoparticle. So in our study, basically we use chemistry methods, chemical synthesis method. काहेकि ना सेटा cost effective और easily जो जगह चाहे वही होते हो ये कॉलेज में होते हो nanoparticle system develop किया है. हमने solve होती cost effective जेतु इसमें हम 50 percent को चमला. हम लोग ऐसे specific sophisticated instrument नहीं, but we are trying to do something based on the available facilities. So now we discuss about what is electronics. So आमे मैंने समझते किसी ना किसी इलेक्ट्रॉनिक्स जिनसे यूज हो, समझता पे मोबाइल फोन अच्छे. So that basically the traditional electronics devices that rely on the transport of electrical charges. इलेक्ट्रॉनिक कोर्स का समझ से और जहाँ सब electrical charge, electrical device function होती है because of movement of electrons. So in traditional electronics, field of electrons have been improved. So recently, scientists are trying to exploit this field digital freedom of electrons. In addition to its charge increases of freedom of electrons, to make a new generation device called as spin-electronics. Spin-electronics, and you have added to spin that called as spin-electronics. So spin-electronics offer an opportunity for the new generation devices combining the feature of standard microelectronics along with the spin-dependent. So pictorially we have traditional electronics that is rely on electrons and ferromagnetic materials that is associated with the spin, and it will combine both electron and spin in a single devices that is called as spin-electronics. So in traditional electronics, that is semiconductor devices, random access memory, integrated circuits like processors, that all are rely on the movement of electrons. And magnetic devices can depend on the speed of the system. So if we combine both these, so we basically develop these spin-electronic devices. Earlier it was predicted, but now it has been realized that spin-electronic devices can be synthesized. It is also being used in our day-to-day life. Information in a semiconductor devices, semiconductor device-based systems can be lost if the power is closed off. Whereas when we consider the electronic devices, it will not this same thing happen, because it retains the information once its power goes off, and it requires more big time. It's much faster than the traditional devices. So people are trying to exploit that. And first, random access memory devices is released in 2006. And in 2016, the size is around 2 MB. Now it is from gigabyte size. So day by day systems are improving, and device functionality is also improving. The memory size of the random access memory is also improving. So still further research are trying to develop, and as you know that initially the computer was like nowadays we are talking about laptops. Laptop का further development है miniaturization है धीरे-धीरे छोटा सिस्टम आगे जाऊँगी प्रेडिक्टिंग होचे पैंटॉप कोरिया में पैंटॉप में छोटा हाथ जो पैंट बढ़े सी साइज भी आसिमो डिवाइस फीचर है। So adding the screen degree of freedom of the conventional charge-based electronics or using the screen degree of freedom alone will have substantially more capability and performances of electronic devices. One need to introduce magnetic property towards semiconductor. ताकि electronics device कोरिया में देखे हमको traditional electronics device के magnetic property introduce कोरिया को in such a way that the semiconducting feature of the system will not be destroyed or it will not be altered. In addition to that, we have magnetic freedom. So that we will implement that material for the traditional devices. So this is really representation of non-magnetic semiconductors. There is spin. We have to introduce spin diluted concentration so that the system will be semiconducting, and in addition to that, it will be keep the magnetic features. So DMS has the semiconductor materials. A small fraction of reverse patterns is replaced by some of the transition metals or tiny transition metal or those systems will have the ferromagnetic features. हमें diluted amount 1%, 2%, 3%, 5%, 10%. बेसी अधिक होने system will change. So diluted amount में less concentration में हमें dopant होगा ताकि वो substitute करेगा। Then immune circuit होगा जैसे ferromagnetic property देगा किंतु semiconducting feature will not be added. So most of the early studies based on the non-magnetic, non-oxide based systems like gallium arsenide or gallium nitride, and it has been shown that the room temperature is much less than the room temperature. So आगुर जो study होगा थोड़े room temperature 0 से room temperature, that looking that one cannot be able to realize this electronic devices. However, the appearance of room temperature ferromagnetic in oxide-based semiconductors creates hope that we can realize these electronic devices. Nowadays, people have already realized these electronic devices. This slide shows the several oxide systems showing room temperature ferromagnetic. So now we discuss about some of the activity of our research. We have synthesized lanthanum zinc oxide with the having the lanthanum concentration from 0 to 5%, and we also synthesized gadolinium zinc oxide by changing the concentration from 0 to 5%, and we have seen that there is no impurity threat for these systems because within the available dopants, dopant sits in the zinc side to make a zinc oxide crystal. ताहले किसी रूम गोटे रूम नेले रूम रे 4-5टा जदी चेयर दिबो हम जदी 5 जन पिला हम 5टा चेयर अछि 5 जन पिला होगा से जाकी 5 से 5 जन जाके चेयर रे बसी जदी 5टा सीट दिबो हम 10 जन कोइबा के बसी 5 जन बसिले आ 5 जन और का चेयर रे ना साइड रे रहबे सो से भलिया हम जब मटेरियल सिंथेसिस करू हम जदी ओपन कॉन्सेंट्रेशन Anti-side substitution होगा कि हमको decide करने वाला है कि हमें low concentration हो कहीं ना तार limited solubility होगी जितना भी foreign atom हो जाएगी particular system रे possible नहीं होगी है ना इतने low concentration लगेगी and I have seen that there is no impedance part क्या तो अभी होने लगे maybe impedance part so surface morphological features have been studied by the three-dimensional development microscope, and we have seen that we have prepared the nano rod type of technology. The length of the about the case as 86 nanometer, our case is 269 nanometers. Our diameter of the first case is 43 nanometers, second case is 50 nanometers. So aspect ratio length to diameter is 4.26 and it is 5.3. Similarly, in gadolinium case, we also seen that the formation of nano morphology, and in this case also aspect ratio was increasing with increasing the gene function. temperature ferromagnetic features. Gadolinium gas also we have seen these types of ferromagnetic features. So in order to understand the mechanism of ferromagnetic field, we have looked the magnetizing as a function of magnetic field to a particular, several models are available to a particular model, found magnetic polar model, and our results are perfectly fit to that model. Based on that, we have explained the occurrence of ferromagnetic fields. So this is a pictorial implementation of how bound magnetic polarization occurs. Bound magnetic polarization is basically a bubble which formed due to the interaction of vacancy with the nearby spins. This means the interaction because of this vacancy served as a charge trap center, and it trapped a charge and free charge and it radiates interaction with the nearby spins. Similarly, two magnetic polar ions bonds, so they will form a bigger polar ion structure. So thereby increasing the ferromagnetic features. So in another system, P times semiconductor system, nickel oxide, we have also nickel oxide is an anti-ferromagnetic system. So therefore we introduce non-magnetic dopants. যেতବେଳେ anti-ferromagnetic order হইব up down arithmetic spin হইব, ଆମେ কোন করଛୁ না ଗୋଟେ up हो down हो ଆମେ ଜାଣିବୁ actually exactly କୋ spin ଥିବ, କିନ୍ତୁ ଯଦି up down ହେଇକି ଥିବ ମଝି spin ଟାକୁ ଆମେ ହଟେଇ ଦେଲେ up down ମଝି spin ହଟେଇ ଦେଲେ up ରହିଲା. So locally we create the ferromagnetic environment by putting the non-magnetic system. Non-magnetic ना spin वाला नहीं चलता है. So up तो down को हमें remove करते हैं by non-magnetic system. So we have up and off system. So locally we generate ferromagnetic features, and we will try to exploit that features in understanding the magnetic features and hence implication into this. So in all the cases, we have seen that the existence of ferromagnetic features. Similarly, we study the magnesium group, zinc oxide magnesium is another non-magnetic system, and we have seen the occurrence of ferromagnetic features. In different cases, like in nickel oxide and zinc oxide case, in zinc oxide case, we prepare the rod cell morphology here. In nickel oxide case, we have obtained the three-dimensional spherical systems. All these dimensions are dimensions therefore not as nanometers. So in conclusion, zinc oxide with n-type conductivity and nickel oxide with p-type conductivity shows room temperature ferromagnetic features. Both the materials first introduced device analysis. Then I'll discuss about anti-ferromagnetic electronics. Anti-ferromagnetic electronics जहाँ anti-ferromagnetic system लेगी ताकि हमें anti-ferromagnetic system बोले पालन करें तो आगुर people चिंता करते people are thinking that the anti-ferromagnetic systems are not of any use. ताकि कहीं की डिस्कार्ड करते ले तार डायरेक्ट relevance अगर बुझा करते वर्तमान जो recent study होती है देखा जाता है जो आपने जो develop करते हैं anti-ferromagnetic electronics लेकिन ये develop होते हैं. That is not unlike the earlier case spin system, it is the composite systems. ଯେତେବେଳେ anti-ferromagnetic material ଟା composite होଉଛି ferromagnetic system ସହିତ ସେତେବେଳେ because of cooperative effect their properties will be drastically enhanced, and that field is quickly developing, and although both are identical but it is based on the nano-composite systems. ଯେତେବେଳେ nano-composite system ବିଭିନ୍ନ ପ୍ରକାରର synthesis କରିପାରିବ, କିନ୍ତୁ ଆମେ simply स्टेप सिंथेसिस मेथड फॉलो करू जोटा कि आर्लियर स्टडी रे जो zinc oxide nickel oxide जेंति सिंथेसिस करू केमिकल मेथड से सिंथेसिस करी हीट ट्रीटमेंट करू हीट ट्रीटमेंट करेला मात्रे फेज क्रिएट होछि. जेतेबेले गोटे अनवांटेड सिस्टम किबा किछि अलगा लोक आसी गोटे घर भितर भल लागुछि बसिया पे जेतेबेले मनकर तम मान भितर भोगराई कॉलेज स्टूडेंट मान आम से बेला माने आउटडोर मेंबर बढी बेले बेले भल लगे. सो हीट ट्रीटमेंट देला परे से जो अनवांटेड एलिमेंट्स गुडा थिबो तका सिस्टमैटिकली लाटिसाइड सर्किट करिया कथा से माने ଚାହୁଁଥିବେ କେମିତିଆ ଏସ୍କେପ୍ ହେଇଯିବେ ବି ଟ୍ରିଟମେଣ୍ଟ ଫଳରେ ସେମାନେ ଫେଜ୍ କ୍ରିଏଟ୍ କରି ଅଲଗା ଫେଜ୍ ସଲ୍ୟୁସନ୍। ସୋ ସେଠି ଯେତେବେଳେ ଦୁଇଟା ଫେଜ୍ ରହିବ ଗୋଟେ ସିଷ୍ଟମରେ ତାକୁ ଅପୋଜିଟ୍ ଆଣ୍ଡ ଯେତେବେଳେ ଗୋଟିଏ ଫେଜ୍ ଅପୋଜିଟ୍ ଭିତରେ ନାନୋ ଡାଇମେନ୍ସନ୍ ରହିବ ତାକୁ ନାନୋ କରିବ। ତ ଆମେ କ'ଣ କରୁଛୁ ନା ଆଇରନ୍ ଡିଭଲପ୍ ସାଇଡ୍ ଦେଇଛୁ ଟ୍ରିଟମେଣ୍ଟ କରିବା ଫଳରେ ଆଡିସନାଲ୍ ଏକ୍ସଟ୍ରା ଫେଜ୍ ଆଇରନ୍ କେସ୍ ଏକ୍ସଟ୍ରା ଫେଜ୍ ମାନେ ଏକ୍ସଟ୍ରା ଫେଜ୍ ଆସିକି ଅପୋଜିଟ୍ ସଲ୍ୟୁସନ୍ ହେଇଛି ଆମେ ତାକୁ ଆକ୍ଟିଭ୍ କରିବା ପାଇଁ ଇମ୍ପ୍ଲିମେଣ୍ଟ କରିବା ପାଇଁ ସଲ୍ୟୁସନ୍। So basically the magnetic property ଆମେ study କରୁଛୁ ତାର application ଜାଣିବା ପାଇଁ horizon that is relevant to the anti-magnetic situation or not, and we have seen that the one of the remarkable features that existence of excess bias characteristic that exists at room temperature. Earlier studies reported that the excess bias characteristic is not exist at room temperature. Low temperature exists. In another set, we are just increasing the annealing hours. With increasing annealing hours, we have also seen the robust excess bias look and although the excess bias characteristic is less, what it exists in room temperature. So generally, but people predict that if you consider the anti-ferromagnetic system and embed the ferromagnetic system in that, if the ferromagnetic system is size or more ferromagnetic amount of physics are there, then that will not be a good choice to implement the system for anti-ferromagnetic spectrometrics purpose because robust exchange bias will not be there. So taku basically ଯେତେବେଳେ study ହେଉଛି ତାକୁ ଆମେ କ'ଣ କରୁଛୁ ନା phase fraction change କରୁଛୁ then magnetic phases କେତେ ରହୁଛି annealing temperature change କରିକି fraction of dopant change କରିକି ତାକୁ study କରୁଛୁ to get information which amount of change fraction is important or which annealing temperature will be helpful to tune the required process. In conclusion, we have seen that the existence of both like exchange bias characteristic which can be utilized for anti-ferromagnetic spectrometrics purpose. Thanks for your kind attention. I am thankful to my PhD scholars because one has been shown in this presentation, and I am also thankful to the collaborators from the CSR Bhograi and my friend Rajesh and I am also thankful to CSR Mumbai Council for Financial Support. Thanks for your kind attention. If you have any questions, you are welcome to ask.
Thank you, sir. Now I request our Honorable Principal, Mr. Professor Vijay Kumar Misra, to offer Uttariya, bouquet and memento to our dignitaries. I also request Professor Prabhujan Malik, MSc, University Balikpada, Odisha, to take the memento from our principal. Sir, please. Now I request Dr. BHS Bhogra, sir, please come to the dais. Now I request Professor Ashwini Kumar Raj, co-founder CEO R.I.H.S. BHOGRAI, to come onto the stage. Department of Physics, National Institute of Technology, Durgapur, West Bengal, India. Sir, please come to the dais and take the chair. Our invited speakers are Professor R.I.H.S Government Women's College, Sambalpur. Our next speaker, Dr. Tripathi, IIT, ISM, Dhanbad, Jharkhand. Our next speaker, Professor S.K. Agrawala, FM University.
Thank you very much for giving me this opportunity. So the first speaker already Professor R.I.H.S His topic is design of nanomaterials for engineering and environment remediation. Thank you. I am requesting Professor Sahu to start your
infrastructure. Second, energy. In terms of energy storage, energy generation. So these are the bigger challenges. And next, health and well-being. Secure and resilient society and artificial intelligence and climate technology. So out of these 5 challenges, mostly my address will be on first 2 parts, that is energy and environment. So let me start with, please follow. So first, before I go to the application part, energy and environment, let me start with the material aspect. So first, we need a material so that we can use it for energy as well as environment. So based on 2 approach, let me start with the carbon material, case study, particular case, carbon material. Suppose I want to design carbon materials, especially for energy application as well as environmental application. So let me start with the best quality we can get it from a
follows vapor, liquid, solid type of mechanism. Where vapor sits on the catalyst where at a particular temperature, then by forming a eutectic alloy, once that eutectic iron preheated and further growth, that forms the carbon nanotubes. And if I look at the finding the literature, basic mechanism for the growth of CNT is catalyzed by transition metals and non-transition metals like palladium, platinum. But some other sort of catalysts are also there in the literature that do not able to explain the mechanism of growth in terms of VNS time. So the question arises, how can we able to explain the growth of the CNT based on this mechanism? Once you are able to explain the growth, then design the mechanism. So let me start with frame 4 questions. What are the questions? How important is the carbon solidity? How is the melting point of a metal is important? Do we after need a catalyst as a catalyst? Is the catalyst a catalyst? So to address all these 4 questions, what we do? We took several varieties of catalysts, then we synthesized in a particular condition. Start with a low melting. So low melting bismuth, melting point is 298, but it could catalyze the growth of CNT. It's a moderate melting copper, it could also catalyze the growth of CNT. High melting silicon carbide, boron carbide, these are also carbides also catalyze the growth of CNT. Then comes the 5 oxides, basically alumina, titanium, those are also catalyze the growth. Then we did a compatible measurement, and what we did, we took some high 3 nanometer, 4 nanometer germanium nanotube. Then we able to grow single wall carbon also. So what we basically conclude from this, then we do 2 systematic studies. One, we took all silicon dioxide and anisotropically LPKOH and created some group. Then we grow the CNT on that surface. What we found, there is also growth of CNT. Then to understand what's exactly going on, we took a bare silicon substrate, mass to one side, and another side KOH anisotropical edge, and to be further growth of CNT. What we found, the OH surface is not catalyzing the growth, whereas edge surface catalyzes the growth of CNT. What is the basic meaning now? So what we got the result, irrespective of type of catalyst, melting point, carbon solubility, we could able to grow CNT by simple creating nano surfaces. Once you are able to create the perfect nano surface, we can catalyze that surface to grow CNT. So with this basic understanding, we could able to design various type of nanomaterial. This is a side growth of carbon nanotube. It's a row type of CNT. Then graphene, 2-layer graphene. Then the vertical aligned carbon carpets without any surface bias. Then a very interesting nanostructure between 2 silicon nanopillars which act as a very tiny mass sensor. Next. So additionally, with those ideas, we are able to know various types of nanostructures, especially for sensors and applications. Now, I will come to my second part of my talk, that is your interest. So, now we got the idea, how can we design the material? Now, we have to use it to recent research area, basically supercapacitor and environmental remedies. Let me start with the second part, energy. So, the device supercapacitor. We know capacitor, we know battery. So it is the in between factor, in between device, that is supercapacitor. And charge your mobile within 2 minutes. So how, before we go to, if you look at the research gap between the supercapacitor result, then it is not going to market because of its energy density is quite low compared to the battery. Suppose you need a device that works for longer time with a perfect energy density. You need a perfect energy. Suppose it's a winter morning, your scooter is not starting, your battery is totally discharged. What you need exactly in that time? You need a supercapacitor. You need a power brush to create the device so that it can start in the initial start. So, based on three things, based on the research need for now, we design materials especially for supercapacitor application. How can we increase the energy density? How can we reduce the cost? Looking into the environment aspects into account. So, the basic need is here. The time, lifetime, charging time, and working temperature. So, it is far away from battery. It can replace battery. So, go ahead. So, the first one, we designed some material. Basically, if you look at the literature, antimony cell line. It's a battery material. What is the big problem is, once you start with measurement, you start debating. So, what we did to achieve that theoretical value, we designed the antimony cell line inside the carbon. So, we anchored up and encapsulated the antimony cell line inside the carbon matrix to form different electrodes of the supercapacitor. With that, we could able to achieve the energy density to a large extent, that is up to 48 watt-hours. The second part of the talk, where the PTA, polyvinyl alcohol, which is a hydrogel, basically we use that hydrogel to create a meta-acrylate surface. That meta-acrylate surface will enhance the supercapacitor efficiency to a greater level. Basically, if you look at the literature data will be far less than our data reported using a simple hydrogel as a catalytic agent on the surface of molybdenum nanoparticles. Then flexibility is the another issue. If your device is not flexible, so applicability will also reduce. So to make energy good, what we did to simply took the fabrics, the cotton fabrics, and on it we designed the material, basically the biometallic organic framework, and simply arrange and create two electrodes that are different as a cathode and an anode for a supercapacitor device. But this work is under review. But very interesting work. Why? If this work is, this will give us the idea how we can create a flexible supercapacitor using a brass material. Why brass? Let me start with my next page of talk. So whatever we studied, we got the samples in lab. So what we need basically, we need to transfer the technology from large scale to a market. So what we target is simply transfer technology. How can we use the waste material to bring it to technology? So whatever we are getting the materials very small, tiny scale. So meeting of material working for a longer time, more than 12 hours. So can we able to design a system where we can get a ton of material just within the 5 minutes? Yes, it is possible. So what we did, we basically designed a system that's called plasma reactor, where we simply the waste polystyrene what we are getting in our home appliances. When your home appliances coming to your home with a packaging, with a foam, that's a polystyrene. we use that polystyrene simply, please go to the next. Polystyrene and simply modify the polystyrene to nitrogen-rich carbon material which acts as an anode for supercapacitor electrode. And you can able to process the material, that is high PTF material, within 5 minutes to this sort of property. Then this is the performance of that polystyrene after conversion to a nitrogen-rich film material. So its stability is very high and it's consistent. So next, another material, which is an industrial waste. So what we did, we already got the electrode from brass, that is polystyrene to anode. What we need another one, we need a cathode. So what we selected an industrial waste. What is that waste? Trace aluminum. So that is called aluminum dross. So we took that dross and simply chemically modified that dross, and then we took to carbon material. And this is the dross, and we converted to a high value, high surface area conducting network which acts as a very robust supercapacitor cathode electrode action of positive side and negative side. Now what is going to how to design the device. This is the performance. Now I part of my talk. So what we did, we designed the material, we execute the energy. Now another use of case study I will show how we can modify the simple trans element. Suppose you have a bond nearby to your home. It is totally polluted. You need some powder. Throw that powder on the surface of the bond. Then within factor of second, by the use of sunlight, it will purify the bond with usable water quality. So how can it be possible? This is called visible light photovoltaics. So what we need? You need to create a material. So material is important. So to design that material, what we did, we took the accumulated blue dust. You know what is blue dust? Red one, basically the nali mati. The heather for the fact that iron content is more than 80%. So we took that trace, our waste material, then we created the iron oxide. Iron oxide, by iron oxide, it is readily available. Waste can convert you well, as well as very interesting thing, it absorbs the acidity of the water very quickly. So we took, because it has the visibility on the within the yellow red, that means the visible red. So we took that material, another additional material to form a nanostructure is what is gold. Why do people use silver gold? That's a very clever. You know, girls are very clever because they are using gold, silver, platinum. Why? Because it will not form the oxide randomly or within easy way. So we use that in school. Simply we use gold as a hybrid material. So it is got a conducting path as well as the visible light absorption material. So using that as our crystalline material, we assemble the grounding surface. Then we use the photographer at a distance. So back. Okay. Let's take the photocatalysis is in visible range. We use the sunlight. The sunlight just takes a reactor to the sunlight, and there we form simply it has a simple dye which poisons water quality. So we, as per experiment, we took the dye and simply added some catalyst, what we designed, and to it in a visible irradiation for few minutes. Then it converts simply the complex molecules simply decompose to the final molecule, which is not hazardous to the environment. In the second case, as we just discussed, first is gold, second is repellent. So I also do that repellent, and incorporated in manganese. So where we got the manganese? Manganese from manganese noodle. So it's an industrial waste basically. So using that noodle, I designed a material for the graphene oxide substrate, and it creates a high heterostructure and converts the visible, the poisonous catalyst, poisonous element, implant molecules, or changes the water molecule. And these are my references. Next. So thank you for your attention. I actually acknowledge my collaborators from this institute. I acknowledge Department of R.I.H.S for funding my parent institute for academic support, and the team, organizing team of R.I.H.S for giving me the opportunity to present my work. Thank you. Thank you.
Thank you, Professor Sahu, for your nice presentation regarding design and applications of nanomaterials, including one-dimensional CNT and two-dimensional graphene. Thank you, sir. Now, question session. Any questions from the students? If you know more questions, let us thank Professor Sahu again for a nice presentation. I hope the students will be benefited from his talk.
Thank you.
Next, Professor Umakanta Tripathi, IIT IISn Dhanbad.